Well, hey there, everybody. Welcome to SkyTour Livestream on this January 27th, 2022. It's a year that promises lots of cool things for us, including the thing we have on the screen right here. Before we do that, let me just bring in our amazing astronomer. This is Daryl Mason. Hey there, Daryl. How are you? Welcome to SkyTour Livestream.
Hello, Mark. Thank you. Hi, everybody.
Yeah, we got a few people watching already. I want to say hi to Michael Klages, who's here. Donald Kunzer's here. PG is here. Hey there, Petita. And Tim F. All right. Woohoo, Tim F. So we're actually going to start off. I started off with an object already just to have some fun. You can see this dark cloud actually materializing. This is only a 15-second exposure. It's we really need to take a longer one. So what I'm going to do is I'm going to clear this stack and take a longer exposure of this. All right. And what it is interesting nebula, and it's called Hind's Variable Nebula. Not like the ketchup, but a interesting little dark nebula that has a emission component and a semi-reflection component. All right, so that's this guy right here. All right, now we're gonna go back and let me show you how big this is. This is the full frame view of it, but here's the actual wide angle shot of it. So when you look at this shows you just how big it is. You can check this out. It goes to this whole area here. Isn't that incredible? You know, so we're going to be able to capture the entire nebula. That's why the nebula is sort of off to the upper right there. But the first thing we're going to do is clear this after I set the exposure from 15 seconds. We're going to add another, another 15 seconds. We'll say 30 seconds for this guy. All right, and here we go. Now I'm going to clear the stack, and the 30-second shot is going to come in, and we're going to see the new version of this. Okay. Hind's Variable Nebula comes in one variety, actually two varieties: dark and dusty, and red emission. It's really beautiful. So here it comes. So Daryl, how's it going out there, by the way?
Oh, it's cold, darn it. We
Yeah,
had another storm come in this morning and today, and they've been moving a little bit north of us, so we don't really get that much snow. Might have got an inch today, but it's cleared out now. It's supposed to get down to single digits tonight, and it's headed your way.
Excellent. Yeah,
yet another nor'easter is
that.
what they're saying.
Yeah, I saw that. We may end up with that. You're right. Ay, ay, ay. Oh, look, I think this goes over here, too. I think this is all one big patch. Let me get rid of the name here for a minute. Go away. Okay. Maybe not, but I think there's an additional patch over here of nebulous dark nebula, and then some here, wispy there, and then it goes up to that. We're in the constellation Taurus, by the way, and this rough look is going to go away as soon as we get more data. Izabela, welcome. Good to see you. Daisy and Zoe, hi. Nice to see you as well. Izabela says she's working as well. Well, that's cool. Red Dragon, hey, how you doing? Welcome from Oklahoma. That's pretty cool. I was in Oklahoma City a few years ago. Pretty cool. I actually was in the hospital having a surgery. Actually, I had to go down from Connecticut because the specialist was there that could do it. And I got out of the bed, having had surgery, was barely able to walk. I hobble over with the IV stand to the big window at the end of the tallest floor, that special ward for out-of-state patients. And I look out there and I see these dark clouds, second satellite, and I asked the nurse, I say, those aren't tornadoes, are they? Yes, we may have to get everybody down to the storm shelter. What? I could barely walk. It took me like 15 minutes to go 25 feet. And she says, yes, there's 6 tornadoes in that dark wall of cloud. I went, ha ha ha, okay. And I start going back to my room as fast as I can. It's like, luckily, they dispersed and went different ways, and they didn't have to evacuate the upper floors. But they say, yeah, we go through this every day. Oklahoma.
When the winds come sweeping down the plains.
And the winds can knock down the plains.
Yeah. They do get some piercing tornadoes, sir.
Yeah. We have 2, these are probably both Starlink satellites right here. One here and one here. I suspect I'm expecting to see a Tholian web here, like crossing across and going this way. Because that's how those satellites are designed. They're designed to have overlapping ranges. But the nice thing about this software that we're using, it's stacking these images. That's why we're just sitting here. It's not like we're doing nothing, because it takes an image, aligns the next one, and then stacks them on top of each other. And we get these final stacks. So if you look right down here, you can see that we've stacked 7 so far, now 8 images. You'll notice that the noisiness, that mottled texture, is going away. And that's the benefit of using software like this to stack. And the other benefit is the satellite trail was only on 1 frame, and we're stacking additional frames over it. So that is errant data. That's data that we would like to see go away. So the more we stack, the more that trail is going to actually go away. To prove it, this trail down here, this happened first, and then this one happened. You'll notice this one's fainter than this one. Okay? It was as bright as this one, but now, as more data comes in to replace that bright trail with the black of space that should normally be there, it's going to fade away over time. So we can auto-remove these trails by just simply letting the software do its thing. It's the best of both worlds. But sometimes they're very big and bright, and we can't get rid of them too easily. We definitely have an additional cloud over here, Daryl.
Yes,
it looks
you
like
do.
it trails under here.
Looks like you're starting to get some definition in that cloud around
I can see that, huh?
the right part of Hind.
Yeah. Yep. Alright, one thing I'll do, let's do a color. I'll do a color balance here. It's a little bit green. I'm going to get rid of that green. There we go. And that showcases the brownish color of the cloud just a little better. See that?
Yeah.
Wow. That's nice. Yep. And the thing that I've talked about a number of times is when you look at the cloud like this, okay, you can see that inside the cloud, the stars look red, right? And as I zoom in, you'll see what I'm talking about. Okay. You see how these stars look a little bit red, right? The cloud has a way of actually causing these stars to have their light reddened in the same way that the atmosphere reddens the sunset, the sunrise. Same principle. When there's a volcanic eruption, the sunsets are a blood red. Well, in the same way, these stars can be reddened to be blood red by dust, not in the atmosphere, but dust in interstellar space. But we're talking about a cloud here that is a number of light years across. Light years. So, from the very beginning of our space travel days, had we started on the left end of this cloud, we wouldn't even be a tenth of the way across this cloud at all. We would actually be far less than that. So, we actually have a lot to look forward to technologically. But the point of that was that these clouds are big, and so even though there's only, say, 300 molecules in this dust per cubic centimeter, okay, a cubit like a sugar cube, okay, you have a tremendous amount of depth to this cloud. it's going through a lot of molecules overall because it's a very, very big cloud, many light years across. So this is a variable nebula. It'll change its brightness depending on what's going on with the star. But you can actually see very clearly that this star is doing the illumination of this cloud. This is actually a hydrogen alpha region. It's not glowing by reflected light. It's actually making its own light because the star is ionizing the hydrogen atoms that are nearby, and that ionization is going to cause this to be cause the hydrogen gas to glow. All right, so that's another thing that happens within these nebulae, and we've talked about this before. It's really cool. There's a faint trail right here.
Star in the middle is T-Tauri, where the name
T-Tauri.
T-Tauri stars come from.
That's right. Yep. And the T-Tauri stars are the ones that we see inside the Orion Nebula. They're young, hot stars, and you might say, well, why are they called T-Tauri stars? Well, because T-Tauri, T dash, letter T, capital T dash Tauri for Taurus, T-Tauri. And the T-Tauri stars are these young, hot stars that are have passed their protostar stage, and they're on their way to becoming full-fledged stars. And so when stars are born, they can actually be somewhat irregular. And we notice with T-Tauri stars that they're not perfect stars. They stand out as different. And so that's why we name stars like that T-Tauri type stars. So we'll see T-Tauri type stars in the Orion Nebula.
And it's also 3 stars.
Yeah, I see one here. I'm not sure if we can see the other components unless it's spectroscopic. There might be one there. Can't tell.
I think what we're seeing is they call it T-Tauri North. T-Tauri South is evidently mostly visible in infrared.
Okay.
And I haven't seen anything about the third one yet.
Okay. Let's go back out to let's take the full frame and shrink it down to fill the screen here. Well, now you can see that there is definitely dust all throughout this region, and the more we stack, the more you see it. Okay, and notice the satellite trails. Little by little, they're going away. This was very bright, and now it's getting less and less prominent. And this is all a 30-second exposure. And we could actually take this and do an additional stretch on this to kind of bring out what's going on in there. And you can really see what's going on. We're not going to leave it like this. But if you look, you can see, if we do this, you can see the extent of the dust. It's all throughout here. You can see this dust is all throughout this region. So that's just a little hint of things to come. So let's drop that out of there. And just go back. Let's go back into our stack parameters and see if we can't tease out some more detail in here. Yeah, there we go. Just a little bit more. Okay, we've stacked 23 of these. And we'll go to 24 and then move on. I want to show you where this dust comes from. Okay. So let's get up here and get ready. And for those that haven't seen us before, each of these images we take two kinds. We take a astronomical FITS file, which is an FITS file, and we take a PNG file. Now I'm about to do that. You're going to see a save right here, and then across the top of the screen right there you see the name of the file. Well, if the file shows up there, it means it's on its way up to the server from the observatory, and it's heading to our public server where it'll be available for you to see in, well, hopefully just a few minutes. And the next file that I took is just a ping file. I'll do it again. A ping file is a regular graphics file. I'm going to save it exactly as seen, as you see there. And again, you'll see the notification across there. And that's going to show up on the server too. So the public server is available for all of you. You can just go up there. It's read-only. You can't hurt anything. You go in, you can take the pictures, download them. They're big. These are big pictures. So you're going to shrink them down probably to put them on a desktop wallpaper. And what you'll find is that if I deem them worthy, and most likely I will probably process these further. And then after I process them further, I will upload the processed one right next to this one right here that you're seeing. And so it'll be there too, and you'll be able to take it down, and you'll know it's the processed one because it has the name in front of it, not just this cryptic indicator which it'll have. So this is cool. All right, so there we go. Beautiful, beautiful cloud there. And I'm gonna hit clear, and it's gonna go away, and you're gonna say, "Oh no, it's gone," but it's not. It's not gone. So we started off then with Hind's variable nebula, right? And in case you're wondering again, this is what that was, Hind's variable nebula. All right. Okay. Now we're going to go to a different object. And it's an object that's going to kind of show you where the dust that you saw at Hind's can come from. All right, so we'll do that right now. All right, so and as a little bit of a tour, up top, up here, this is the telescope control. That right there above my head, that's the telescope in the building. That's the telescope sticking up. That's the roof of the building right there. It's off. And then right here, this is the telescope computer. Of course, that's our planetarium view that is actually doubles as a telescope control system. We don't need it. We could do it from this, but I like doing it from this because it's really kind of cool to see it. And then the background, of course, is our view. And you saw the camera control on the right side over here, which we'll see again in just a minute. So let's go back out of this. Yeah, Starlink could get out of hand, but I suspect as long as we can deal with the fact that we're going to have some satellite imagery, satellites, we're gonna be able to deal with it. I don't like the fact that we have to, but if we want to have fast internet, okay, right now you'll notice there's like a 1 to 2 second, sometimes 3 second delay with everything I'm doing. And it has to do with the fact that I'm trying very hard to get things in the view, and I've got to be able to think ahead and anticipate what's going to happen. You know, it's really crazy. Okay, there you can see the telescope is slewing. It's moving. You can see star trails forming up there on the screen. And let's go into, this is my hyper mode I'm going to go into, which actually shows it like a night vision finder, essentially. And you can see beautiful stars. This is Zeta Tauri right here, Zeta Tauri, the star, and it's going to center it up, and it's going to use it as a little signpost to navigate to this guy up here. That's where it's going. So you'll see this come down.
Can already see it.
Yep. So this is going to come down right here. There we go. And then it'll stop, and we'll be able to capture this beautifully. Okay, so once that gets in place, we'll center it up, which is something I like to do. All right, and get it ready. So let's just get it close. We don't have to. It's not necessary to do this, but I like getting it this way so that it kind of frames it a little better. Here we go. Okay. I know I haven't shown you guys this too much here, but I use this privately a lot. Okay. Okay, there we go. That's good enough. All right. So now I'm letting my telescope get a guide star. It takes 11 seconds for it to get a guide star. And while it's doing that, I set up the exposure in the camera control system over here. So the exposure on this is going to be 35 seconds. I don't need to go 35, but I will. Hey, Zatarak, how are you? Good to see you, man. And then it's going to run off and go. And during that time, I'm going to set up the image stack, the successive stacking of the images. And that is going to provide our beautiful images. What's a snipper scope, Donald? While we're waiting for him to answer, here comes the first Crab Nebula image. There it is. And it's actually too bright, but you know what? I think we can adjust it down. Yeah, I'm going to take it down a little more. That's what you get when you have a really good dark sky sight. You know, you get objects that you're used to taking long exposures with, and they don't need them anymore. It's so dark that, you know, you get these really dark images right off the bat. This will work fine. This will be great. All right. So we have a second one coming in, and that's going to sharpen it up by at least 50% in terms of its quality, and then its successive amounts beyond that. So we'll go to 75% of the size of this full image. So we're going to zoom in, and now we're looking at the Crab Nebula. Now, when I talked about that dark dust before, this is the kind of thing that caused some of that dark dust. Not in that particular region, but in general. This is a supernova remnant, the remnant of a star that was heavier than the sun, probably 8 solar masses or above. And the star ran out of hydrogen and helium and carbon and other elements that it was fusing to make energy. And when it ran out, it finally reached a limit. And that limit meant the star could no longer hold itself up with this outward radiation pressure. And the massive gravity on this massive star won out. And the core began a process called, well, as you can imagine, core collapse. And the core collapse ended up with the outer core of the star smashing into the inner core and onto itself. All right. Meanwhile, the outer layers of the star start heading in as well. But when the inner core, this outer core smashes into the inner core, it bounces off and shoots back out at a high velocity. And that collapse actually takes place a quarter of the speed of light in speed. At a quarter of the speed of light, that's fast. And so when it does that, that outward motion now, all this material that's deep inside the star, all the elements that were forged in the core of the star, ends up getting spread to the heavens, because as it shoots back out, you've got this stuff coming in, you got this stuff shooting out, it rips the star to pieces and causes this massive explosion like this. And the supernova explosion is one of the universe's quintessential cosmic killers. If there was one that went off close to us, it could doom us, even though it's light years away. But luckily, there's no stars nearby us that can go supernova. The closest that can go supernova, I'm thinking, is it probably one of the stars in the Pleiades, maybe? I'm not sure.
Say that again.
The closest star that could possibly go supernova. Everybody knows Betelgeuse at 750 light years, but possibly one of the Pleiades stars. Because they're what, 240, right? Light years?
Pleiades, I thought they were about 400 light years away.
Oh, 400, that's right. Okay, yeah. But they're very hot B stars that are destined for supernova dumb
Yeah.
at some point. So, so
Boy,
I think
that would
at the
that would
moment,
really light things up if one of them went.
I know. I think it's got a ways to go because it's a young cluster. It's got a little bit of life left.
Mhm.
Yeah. And when
If
you
it was
see,
still
I mean, when
inside
you, if
that
you,
dust cloud.
yeah. Well, see, the thing is that the Pleiades stars were born somewhere else, and as they're drifting around the galaxy, they actually just happen to be going through this dust right now. They weren't born there. That
Right.
dust actually has nothing to do with it. And
Right.
you say, well, how can you possibly tell? We can tell because we can analyze what's called the proper motion of the stars. That's the actual motion of the stars, and the motion of the dust is something different. It's going a different way. So if they're all traveling together, then it's part of the same cloud, but they're not. They're crossing paths. They're
Yeah.
ships crossing in the night. Hi, Marianne.
Yeah, Marianne is here. They used to think they were stuck in that dust cloud, but now as you said, they figured out that it's passing through.
Yeah, and it just took a good analysis to figure out the motions of the dust. Hi there, Judy. Judy McClelland is in the house. Good to see you. Well, I see your name. I don't see you. You see me. Okay. Marianne, don't call me a dork. I just heard Marianne call me a dork. Anyway, so this is the beautiful. This is our beautiful supernova here, and I'm trying to figure out where you got a. Okay, here we go. There we are. Okay. That's why. Okay. If you notice, you see all these beautiful tendrils in here. This is something else, okay? Hey there, Boozy FN. Hey, great, man. Thanks for subbing. That's fantastic. I'm glad you're here. Did you see the announcement in one of the astronomy Facebook groups, Boozy? That's just curious. We're looking at a supernova right now, so that's hopefully you heard what I was saying. That's pretty cool. Now, we have a lot of regulars here, a lot of people that take care of you. They can answer questions, and they're also, we're very, we're very interactive. We talk to the people in the chat. Sometimes we actually bring them in. So, that's how it works. Oh, great. Thanks, Boozy. So it works then. I was trying something new, trying to put the announcements in some of the other chats, but isn't this a cool environment? I mean, this is live. This is live. We're doing this live. And I really love it. So let me just remind everybody, I'm zoomed in by 75%, but this is the entire field crunched down to fit in the frame. That's what we've got. And just so you know, this is 4 full moons across. Okay, the moon's half a degree basically. That's 30 arc minutes. So 30 and 30 is 1 degree, and 30 and 30 is another degree, and then it's 3 moons tall. So we have 30 and 30 and 30, right? So it's 3 full moons tall and 4 full moons across. That's the size of the field of view we have with this telescope, but it supports a native resolution of this. This is 100% right there. So this is 100% zoomed in, and it still looks pretty good, So it's pretty cool. And that's 75% actually. And we have on occasion brought it up to 400% just for purposes of checking something out. And here you actually see this color modeling. This is noise, and we always try to get rid of the noise. And the more we stack, the more stacks that we do. We're making successive sandwiches of images that are all stacked together. The more the noise goes away, and the much better it looks. So let me pop this back out to where it's a little more usable. And then I want to show you one other thing, which I believe we can see now, but I'm going to bring us to 100% to see this. When the supernova goes off, one of the things that happens is a lot of this debris goes out from the star. But as it goes out, it cools. And sometimes the hydrogen can form molecules of hydrogen, diatomic hydrogen molecules, little molecules. Also, there's a lot of carbon in these stars that are made in these stars before they blow, and the carbon can make a carbon molecule. So you have like a CC, a carbon molecule, and carbon, we know, is the basis of life as we understand it. So we look here and we look at a supernova like this, and we see that we have a lot of carbon, we have a lot of hydrogen, we have other gases. These colors mean something to us. Colors like this mean potentially hydrogen gas being excited to glow by the remnant of the star that's left in the core here. And that remnant in this case is a neutron star, but a special class of neutron star called a pulsar. It's a rapidly spinning neutron star that has hot spots on it. And every now and then, as that flash passes us, we get swept with that light. So it's like it's like getting slapped by this star. All right, it just happens that every now and then for this particular star is 33 times a second. That's how fast the star is rotating. And by the way, that remnant is about the size of Manhattan Island. So the universe, it be crazy, man. But let me show you a little more detail here, because there is the pulsar right there. You can actually see that remnant, but we can see it better if I drop the brightness of the center down just a little bit more. Okay, see that? Okay, so now by dropping that brightness down, you can see the pulsar right there. That right there used to be the star that a bright glowing star here. This was probably one of the brightest and bluest stars in the sky. Now it's this tiny dot that you can barely see. But let's be clear, it's thousands of light years away from us. And this tiny star is only the size of Manhattan Island. So it's got to be pretty darn bright, right? And it is. It's also very compact. A teaspoon of that material here on the planet Earth would weigh over 1 billion. That's billion with a B, as in beta, 1 billion tons. So we're talking heavily compressed material. All right. But you can also see these beautiful filament structures, these green filaments, these green tendrils here. These are oxygen, ionized oxygen, doubly ionized oxygen. We call it O3, O Roman numeral 3, And this is the hydrogen potentially over here. It could also be neon. It could be some of the other constituents, right? And those are the materials that the star is made of in the hydrogen case, and stars that the star can make, or elements the star can make, like the oxygen and the helium and the carbon. And that carbon that we talked about with the dust we saw in the previous shot, that's like soot. It's like fireplace soot. But made in the stars. Now, interesting, because when you talk about this, you have to realize, and I think most of you realize, we are in fact made from the things that were originally made in the core of a big star. Everything that makes you, every single atom in your body was once made in a star. And you know what? You're only the current user of those atoms. Those atoms went on a real circuitous journey through the universe before they became you. And that problem, what we're talking about when I say that is the atoms spent a lot of time doing other things besides making you. And you're not the first one to have used them. They were born in stars. They also could have gone into other stars. You might actually be like the 5th or 10th, 100th generation of these objects, of these atoms. So it's actually kind of cool to think about, Let me just do this here to bring it down. So that's the beauty of the universe. The universe spends it has copious time on its hands, all right? So we don't have to spend too much time worrying about all these things. But I'll tell you one thing: it is interesting to look at the genesis of and the creation of these elements and where they come from. And you remember your periodic table from maybe high school or college or whatever. We dealt with the periodic table for all kinds of things. I do have a degree in astronomy. That's what I decided to go to school for. This is what we look like as an astronomer. But I can tell you that they are really interesting objects out there that we look at, and a lot of them are things that we didn't understand, but we understand them a lot better now, and I think that that's something that comes from the fact that we've done our diligence. So we're still doing this right now, so we're going to keep working on this guy. Okay. So I'm glad to see that you guys, some of you have found us from other Facebook groups. And I had some people tell me I gotta work on the Instagram groups as well, and I will. I'll be working on those as well. Let me tell you, it was enough to get this thing up and running. Daryl's been through this. He's been part of this kind of. But in the chat here is Marianne Robb, and Marianne is actually integral to the workings of the Sky Tour Livestream Observatory, and so is Tara Diulis, who unfortunately is not here today. But they are both very important to the, I'd say, every part of and getting this observatory built. Because with COVID, I could not go out there. I didn't have it, but I had to depend on Marianne and Tara to do it, and I've never seen more dedication to the task than they showed. It's like, wow, and that's why I say, Sky Tour Livestream rapidly went from just me to us. Daryl's here all the time. He's a font of knowledge too. Marianne is here in the background working, and in fact she'll run out to the observatory if there's a problem, as would Tara. So let's see what we've got here. We have 28 stacked here. I would say that's good for now. So what we're going to do is pause it and save it. Just as save the stack, you'll see the green line across the top. There it is. And then I will save it exactly as seen, so you can get this exact photo waiting for you on the server if you want to go check it out. Remember that little tiny white dot in there. That little tiny white dot, that is the remnant of the supernova left over. Because when a star blows up from a supernova, it leaves either a neutron star behind, which could be a magnetar, a pulsar, or a black hole, which is another thing that it can leave behind, in which case we would not see anything here. All right, but there's a theory out there that says that all galaxies have a supermassive black hole, an SMBH at their center. Supermassive black hole, SMBH. As an astronomer, we love to send you all these acronyms and just confuse the heck out of you. All right, so this is good. We've seen this. We're going to clear this now. And then we're going to go over and go back to our 1 second. All right, and 1 second hybrid mode, so we can actually see it very, very brightly. Let's try and do this here. Yeah, I didn't think that was going to work. trying to get into the stack. Just a sec. There we go. That ugly image. I remember when I was first working on this stuff, I ended up writing with a friend of mine named John. I wrote a image processing program. And in the very beginning, the Hubble Space Telescope group was actually using our software to process the images. And we thought it was pretty cool. We called it Process Pro. And there was nothing pro about it, I can tell you that. It was really it showed things really badly, but it was better than not seeing it at all. And they liked it for what it did. Now it's so far beyond us; it's light years ahead of us, so it's great. Saves me the trouble. Okay, this guy, I'm gonna move over. Here we go. I've been. Let me explain how the whole system works. We actually have a back-end system that connects to the observatory from here, and it's another host software that allows us to connect and use the computer in that building as if we're sitting in front of it. But every now and then, that back-end system has problems. It's not our doing; it's the software maker's fault. So sometimes we have issues, and we did have one the other night. We had to shut down the stream because it kept crapping out, but it turned out that it was their fault, not mine, and we got it back, and we could get it back just long enough to shut it all down safely. Luckily, it's not going to rain or anything there. It's actually, right now, there's not a cloud in Arizona at all, anywhere. Jeez. All right. What should we look at now, Daryl? What would you like to look at?
I forgot.
All right. Because I have some ideas. We tried to get this the other night, and we couldn't because of the fact that there was a lot of wind buffeting the telescope around last night. Actually, the night before. And so I'm going to try and take it and do it tonight. We want to get the Spider Nebula and the Fly Nebula. And we'll see them in one shot. That's what's good about this. All right, so let's do that. So I select it. All right. Hello, Vera Lucia Campos. How are you? Welcome to you. I'm glad you're from Brazil tonight. Actually, you're always from Brazil. But see, we have viewers that are from all over the world. James Dugan, see him up there. Good day, Mark and Daryl. All right. As you can imagine, James Dugan is from Australia. And then we'll see David Schmidt in here in a little while, I would imagine. David is from Bangkok. He's teaching in Bangkok. All right. So this is where we're going to go next. We're going to go to the Spider Nebula and the Fly Nebula. The Spider and the Fly. So now with our hyper mode here, we're just going to tell the telescope to go there. All right. So you see it now, and the telescope is now moving. Yeehaw, leaving trails. And it's going to find a bright star, put that into the view, and from there it's going to star hop. It automatically knows where to go. So this will center up over here about. This is Elnath. Interesting, the spelling here, Daryl. It says Elnath, yet in Stellarium it's Elnath. Are those two different stars?
Can you show me that?
Yeah. can't yet, I guess. All right, I'll come back to it because I can't.
All right.
I'm looking at a degraded internet speed right now, so I don't want to take chances. I'm up to like a 3-second delay here.
That's fine.
All right.
El and Al, I mean, they're both Arabic. I think they mean the same thing. Means the, just
Yeah.
like
In Spanish.
from Spanish. Yeah, like El Paso, Texas, or El Paso County here in Colorado, where I live. El Paso just means the pass, like a mountain pass.
Like L is the masculine form, and Ella, E-L-L-A, is the female. You know. Okay. Okay, I see. We're just waiting here for this to crispen up. All right. I've noticed that at certain times of the day out there, the internet does get slow. And this is Viasat internet, and so it does get pretty slow sometimes. So we just have to struggle through it. Let's try to do a 25-second shot of the Spider Nebula here. And luckily I know where all these things are because the screen is a little corrupted right now. Alright. And then I'll jump in, bring up the stack, and we'll see what we get. Alright, and we'll clear that.
I just had to look that up after you brought it up.
Okay.
What does Elnath or Alnath means? Literally, it means the butting. In other words, the bull's horns.
Okay.
And that makes sense, I guess. Elnath is the other tip of Taurus's horns.
Okay, once the internet stabilizes, you'll see this. This is not. This is actually a result of poor data transfer right now, so we'll just let this get better. And it will. It'll be better and say, hey. So we have three wonderful things in here. We have this cluster up here, which I think is the Starfish cluster. Then we have this down here, which is the Spider. And this here, which is the Fly. And I guess I could frame that a little better, huh? Yes, I could. Okay, so I'm gonna clear that and get out of this for a minute. And I'm gonna frame that up a little better. All right. There we go. And now let's do this. Now what I can do is frame it. So I'm going to move it over a little bit. Here we go. Trust me, it's going to get better. All right. All right, one more time. This is a 1-second exposure that I'm doing, so that's why you're seeing it do what it's doing here. Now I'm just going to go north just a bit to bring the cluster down. And hey there, Corey Williams. Corey, if Earth moved closer to Jupiter, that would actually be a frightening consideration. We would actually be long gone before that, and I'll tell you why. Let's suppose that Earth, could stay warm enough or whatever. It wouldn't, but as Jupiter approached the Earth, let's say that, where the Earth stays where it is, but if Jupiter came toward us, Jupiter is the second strongest gravitational object in the solar system. So it would tug us and start pulling us toward it. And whether we feel that on Earth or not, that would remain to be seen. But the interesting thing is, Jupiter has a magnetic field 20 times the magnitude of ours, but it also has radiation belts. And the radiation belts are extremely caustic to life, let's put it that way. So long before Jupiter got to us, it would loom large in our sky for sure, but it would never collide with us. That is to say, we'd never see it, because we'd have long since been killed by the radiation fields, the radiation trapped in Jupiter's magnetic field. We have the same thing. They're called the Van Allen belts, okay, which Darrell was probably about to say. And the Van Allen radiation belts are trapped solar particles, the solar wind, that gets trapped in our magnetic field and spirals around. And this radiation is something that we do care about, and sometimes, depending on the strength of the output of the sun, sometimes those particles can be dangerous to, say, astronauts in the International Space Station. And there's parts of the Van Allen radiation belts, which are really the Earth's magnetic field that's trapped these particles from the sun. Okay, there's parts of the Van Allen radiation belts that sometimes sink lower in altitude and go higher, and sometimes there's a particular spot, I think it's over the Indian Ocean, where the Van Allen belt gets down low enough such that the International Space Station could traverse enough into it that it could be hazardous to the astronauts. And when that happens, they actually have to retreat to one particular module that has more shielding in it than the others. I don't know which one that is, but I think it's one of our modules. You don't happen to know that module, do you, Darrell? I don't.
No, not offhand.
Okay. All right. Well,
there are some people might have seen these before. Some rather fanciful travel posters of, say, visiting the moons of Jupiter, like Ski Europa, and you know, come see Io.
Yeah.
What they don't portray is that the radiation is so bad it would kill you in short order.
Yeah, you wouldn't be able to even get on the ski lift.
Yeah.
You know, because you'd be done in long before that. Okay, let's do our live stack. We're gonna do this again. I moved it and I made a nicer composition. I put the starfish cluster kind of in the center, okay, and I put the spider here and the fly here, so you'll see it, and it actually looks really pretty. I can tell that our internet is under load out there, so I have to we have to expect that it might take a little extra time here to have a good looking shot.
Could it be your host watching a movie, perhaps?
I don't know. Okay, but here we go. And now the nice thing is, okay, that really cool thing here. And let's see, it's 27th. 3 or 4 days, we should have availability of StarNet. Starlink, sorry. Starlink we were told was going to be ready for us by February. So I'm holding them to that.
You know, one thing I've heard you want to be
20
careful
times
for.
the speed. What?
One thing I've heard you want to be careful for is if you keep checking with Starlink on availability, sometimes they'll bump you to the back of the list.
If you keep checking?
I heard that somewhere. I don't know the truth of it.
Sounds like an internet rumor to me.
Could be.
Hope it is.
Remember what Abraham Lincoln said, you can't believe everything on the internet.
That's right. He did say that. Okay, let's do two things. Let's process this a little bit. Right here. All right. All right, let me just process it this way. Okay. I know that looks lousy, but you give it a second. And then I'm going to process the color. You know, for all the hassle of Starlink, I can tell you, it's going to be a godsend because it's going to give us speeds 20 times this speed. And that's going to be, you know, well, different from what Weird Guy was saying, but it's going to be like warp drive for us. Yeah. Okay. So let's go check this out. Okay, so this is the Spider Nebula and the Fly. And then the Starfish cluster up here. Nice little composition.
W13, there's a lady physicist, cosmologist on YouTube named Sabine Hossenfelder. Sabine Hossensenfelder, if I remember correctly. She talks about stuff like that, what you're asking. Warp drive, how to compress space-time and stuff. She's a really smart.
Yeah, Sabine you're talking about.
Yeah.
Right?
She's kind of funny.
Yeah, that's yeah.
In a very dry German sort of way.
Yep. See, the image is looking better now. This is good. All right, we have stacked 6 images. You can see right over here. It says 7 stacked. All right. So while we're doing this, I can just say, look, there's the telescope in the building. This is our telescope cluster. This is how we control the telescope: north, west, east, south. And sometimes we change the coordinates to things we need. These numbers get us into the telescope computer, which is down here. Okay, and this is our main view. It's beautiful most of the time. And then over on the right side, okay, over here, this is our camera control section. The most important parameters here are this one you can't read. Okay, this is the exposure time. And the exposure time is very important. Here we have it set for 35 seconds. And then the next one is the other one that you can't read because the data has been, well, it's a little better now. But it's called the gain. And the gain right now is set to 350. Now, what is that? The 350 is like the sensitivity setting on your cameras, okay? And as we look at sensitivity settings, what we're talking about doing here is if you take a picture at a sensitivity setting of 50, then it might look okay. Take it at 300, it might be really, really bright because it's overexposed. But with astronomy, we want really over brightened stuff, sensitive sensors, and that's what this camera does. It's a camera that's a specifically astronomy camera. It's dedicated. All it does is take pictures here through the telescope. And actually, usually the cameras are at the back end of the telescope, and they're like, the back end, typically is like right here on the telescope, right? So you look there, and you say, well, there's no camera. Well, that's true. The camera's actually not there. The camera's actually inside this barrel. It's actually right at the end of the telescope, right there. And this tube here is actually a metal tube, and inside that metal tube is actually the camera, all right? And the telescopes usually run like camera lenses. The camera lens can be f2, f8, f6, f5.6 typically for a telephoto or whatever. And our telescope, is also doing a similar thing. When we got this telescope, it ran at f8. Now that has to do with when you look at a camera. When a camera's taking a picture at f22. The opening is really, really tiny, right? Really tiny. When it's around f16, it's a little bigger. When it's f8, it's bigger, right? This telescope used to be one of these, an f8. But if you can get your telescope to actually be at f2, it means that effectively it's bigger and it's faster optically. So in other words, in this example, a nebula like this, where f8, you have to take a picture for about 2 minutes, maybe 3 minutes, to get it looking like you see it here, right now. However, if you take that picture with the telescope running at f2, it's 25 times faster, and we only do a few seconds, and it comes out better than what it might look like at that f8. You know what I'm saying? Exposure. We wouldn't have to use that at all. So, you know, this is really kind of cool. It makes it really neat. It makes it something that allows us to capture more detail very quickly. That's all this is about.
Life is full of trade-offs, though. It's like photographic speed, what you were talking about. F2 is faster than F8 or F10. F2 is also lower power, wider field, and that's where you that's the trade-off: focal length versus f ratio.
Yep. Except I think that as a wide field instrument, it hasn't disappointed me yet.
Oh, I agree. And since you collimated the telescope, it's been able to give you a much better zoom than you had before, so you can still zoom in on objects to some degree.
Yeah. So I'll go to 75% here on this, and let's check out what it looks like.
When we zoomed in on the planetary nebula in M46, for instance, I was amazed how much detail it showed when you really zoomed in on it.
Yeah.
That's tiny.
Yeah. See, we're waiting for. The problem is the data. See, here's where you have lots of data. It looks nice, but where the data is less, it doesn't come in as well right away, and you have to kind of give it time to come in. It might just flash in and it'll be perfect. You know, that's what happens. But typically it actually comes in much faster. But like I said, we have internet is under load out there, so that's making it problematic.
Yeah.
But that's okay. That's all right. Not a problem. Starlink is going to fix all that.
So when Starlink becomes available to you, I mean, is that something you can install yourself, or do they come out and install it for you, or?
No, I can install it.
Okay.
Yeah, I can install it, and I will. I will install this thing. The Starlink dish is actually pretty big, you know, and the nice thing is it has servo motors in it. It moves it around, and it finds where it has to go by itself to track the satellites optimally. And the idea is that wherever it looks, it should always have a satellite in view, because it's got a fairly wide field, and the satellites overlap each other's range, so that when one drops off, another one comes in. So basically, you get uninterrupted internet. At our location right now out there, we have 99.4% uptime over the course of a day. You know, 99.4%. So that's pretty good. You know.
Mark, excuse me a moment, please.
Sure thing. Michael Klager says, my next scope is a F1, F12.5? Are you getting a refractor? I mean, if so, I can tell you right now that refractors give by far the best views of planets and the moon, for sure. Yeah. Oh, Izabela, thank you. What Izabela is doing here is she's actually putting up the location of our server, our live server. And, you know, she's very diligent, you know. Besides being a brilliant artist, she goes out and she checks our server to make sure they're up there, that the things are up there, the objects we're talking about. And when they go up there, she reports back to you and lets you know. I mean, she's, you know, you can't replace someone like that, you know. So very good. So thank you, Izabela. And by the way, if you haven't noticed, in all the comments, the first comment usually on each video is her table of contents, which I move into the description, and so it makes chapters in the video, so you can see what we're talking about, and then just click on it to go see it. That makes it so easy. Hey there, Louis Ta, how are you? This is the Spider Nebula and the Fly Nebula. This is the spider here, and this is the fly. Come into my web, said the spider to the fly. Yeah. And it's got obviously lots of stars. It's a beautiful nebula. You don't steal my images. Izabela says, thank you, Mark, for letting me steal your images. You don't steal my images. We freely give them to you. Because you come up with some really good results. Izabela also does some image processing. As I said, besides being a brilliant artist, and she can actually produce the best images. Okay. We're going to stop this stack right here. We're going to pause it, and we'll save it. And you'll see how it looks when you go to the server. It's pretty good. There we go. And waiting for it to tell me. There it is. The FITS file is there. And now we're going to save it exactly as seen. And you'll be able to get this and download it and look at it and enjoy it. Beautiful star cluster, starfish cluster, spider nebula, fly nebula. Okay, now we'll clear it and go back. Actually, first thing I do is go back here and get rid of the live stack because we don't need it right now. Go down to 1 second again. If you notice I'm looking over here, it's because we have two screens. Okay, this screen over here is the view directly into the observatory. This screen here, over there, is the broadcast software with the chat and so forth. So I go back and forth. Oh, how about that? All right. Welcome back, Daryl.
Thank you.
Okay, so let's bring this up here. And give me my view into the telescope. And let's go check this out now. All right, so
seeing the flaming star up there at the top reminds me, did you have a chance to look at those two images I sent you a link to earlier? The guy
you
had
did
shot
send me
it.
that link.
He shot it and the rosette in the Hubble palette.
Okay.
SHO.
Yeah. SHO is sulfur, hydrogen alpha, and oxygen 3. That's called the Hubble palette. And those are called narrowband filters. And so you shoot in the light of sulfur, which is actually kind of red, and hydrogen alpha, which is a different flavor of red, and then oxygen 3, which is the bluish green that we saw in the Crab Nebula earlier. Okay, a little bit of the green. and then you combine all those three. Those are black and white images that they take, and they combine the three of them, and they make color images from them. And then those color images are then flexible enough to be put into the palette like the Hubble Space Telescope used, which was never realistic. You know, hydrogen alpha wasn't red. Okay, it was more like a yellowish or something, yellow-green, and so forth. So it was very, very different looking. But it was done for the purpose of being able to showcase and look at the differences in the hydrogen alpha versus other elements in the nebula. It was actually a scientific reason that amateurs don't really have any need for, but they do it because it looks like the Hubble palette.
Yeah.
I'm okay with it. You know, I think it's cool.
Oh, they think it's pretty.
Yeah, I prefer the way it really looks myself.
Sulfur.
We're gonna go to the flaming star, by the way.
Okay. Sulfur takes the place. Sulfur takes red in the Hubble palette, and hydrogen alpha is usually a kind of a sky blue color.
Mm-hmm.
Pretty picture, but it's false color.
Yeah.
A lot of people like that, so that's why people do it, I guess.
Yeah. Okay. Okay, we just centered on the star that we're using to head to this object, which you can start to see coming in now. This right here. This is called the Flaming Star Nebula, and it's really pretty. Hi there, DDB. Nice to see you. And C&D Boy is here. Nice to see you, man. Oh, Izabela found our I put up just a few photos showing the observatory under construction. That's up on our server as well. Ah, she found them. I didn't say anything. Hi, Bonnie. Anahata. Where's Anahata? Okay. All right, let's go. See, this is looking pretty high up. This is looking straight up. This is nice. But again, we're under load out there, so it's really not too exciting. All right, let's see here.
I don't actually see Bonnie yet. Is she here?
Oh, well, you said hi, Bonnie.
I said hi, Bonnie, because Izabela said hi, Bonnie.
Okay. Okay.
I see that a lot here. Somebody will say hi to somebody in chat before I ever see that person show up in chat. So I figured she'd be popping up here in a second.
Okay.
Anyway, hi, Bonnie. Just be on the safe side.
Yeah.
Unless D is Bonnie.
No, I don't think she is.
I don't either, frankly, but...
Alright, here we go. Let's do this now.
Make a monkey out of me, Izabela.
Alright, let's do this and clear this. Yeah. Boy, the internet isn't under load out there, man, because it's taking a long time for everything to happen. That's okay. We will struggle through it. That's right, Dee Dee. Of course, D is not Bonnie. Alright, so here is our first image coming in of this beautiful emission slash reflection nebula. This is called the Flaming Star Nebula.
I've always wondered, D, is DDB your monogram? There she is. Hello, Anahata Bonnie.
There's Bonnie. Yeah, she was there. That's nice. Thanks, Bonnie. Good to see you. So this is where we are right now. Flaming Star Nebula. It's an emission reflection nebula. You can see the emission right here, but you can't really see the reflection. It's right there. It's right there. And we've stacked 3 images so far, and this will become clear in just a bit. And we'll be able to perform a few modifications here to actually make this a little bit more palatable. One of those is that we're going to increase the dark level just a bit, right about here. Okay, and that's going to help it show up better. Dee Dee's her nickname, you see that? Deirdre. I knew that.
Okay, that makes sense.
Yep.
Or Mom de Plume.
Nom de plume? Yeah.
Is that like a nom de plume? Are you making a joke, W13?
Oh. Well, I think that Dee Dee is a mom.
Yeah, I know. I was what I was thinking.
Okay. Okay, 6 beautiful stacked images here. This nebula is very cool. This star right here is doing a lot of work for us. Okay, what this star is doing is it's illuminating, it's causing the glow of all this hydrogen gas here, right? And it's doing this through the interactions with the hydrogen atoms that were out here. Hydrogen is 1 proton, 1 electron, and the electron is circling the proton. All right, and as it's circling the proton, sometimes it gets more energy from the star's ultraviolet light, and it goes farther and farther from the proton until it's actually separated from the proton. That's called ionization, where the electron is knocked off the atom. Remember your high school chemistry. And then it'll spontaneously start to lose energy by interacting with other particles out there, and then it may fall into its atom again. And when it falls back into the atom, it gives off a characteristic red light. As it gives up energy, it gives off light. That characteristic red light, in effect, is this hydrogen alpha color, this reddish color that we call hydrogen alpha, or H2, H Roman numeral 2, which is ionized hydrogen. All right, and then next to it, you see this interesting little bluish cloud. This bluish cloud is something in its own right, which I think is really cool. And we're going to go to about 70%, 75% to show this. All right. Okay, so let's have it come in. All right, let me get it up above the name here. Okay. So here's the star. There goes the star. Michael Myers in the corner. Yeah. Dee Dee's daughter says I look like Michael Myers.
I saw that.
Yeah. Well, she could have said I look like Jack Nicholson in The Shining or something, but you know, little victories. So yeah, here in this beautiful, hey there 220, how you doing? I wish I could see a view of a nebula where we could see a video of the nebula slowly moving in the sky. Oh, you know what? I agree with you. And Daryl, if you can find the link, you can show people that link to, say, the Orion Nebula fly-through, which is a cool 3D fly-through the Orion Nebula.
Yes, give me a sec.
That's neat. No worries. Thanks for doing that. Thank you, 220, for reminding us. That's a really good call. And welcome, by the way. Hopefully you subscribed and are part of us now. Okay, if you notice now, we're zoomed in quite a bit here. We're actually at 175%, and I wanted to only be at 75%, so I kind of went a little too far here. Let me just get us back to 75%. All right, so here we go. So it'll back out a little bit and be make more sense. Okay, there we go. So this star then has copious amounts of ultraviolet energy, and it's surrounded by hydrogen gas. It's only one star, though. It's not a cluster, and hydrogen gas is all throughout the universe in a variety of ways, and it's not all evenly distributed. There's clumps of it here and there. There's areas where there's giant molecular clouds, like in Orion. Thanks, Daryl. And in addition, there's dark dust, like we saw with that very first object we were looking at. Well, this is what that dark dust looks like when starlight hits it. Starlight is has a certain effect on dark dust, and what it does is obviously makes it light, right? But we call these reflection nebula. But it's not truly reflection in the true sense of the word, like a mirror. Okay, that implies that the light hitting it bounces back and comes back unchanged. It just changes the direction. It's not quite what happens. The light strikes these dark particles, these dark dust particles, which are usually silica particles, little silicon and other particles, and it gets absorbed by these particles, and then the particles kick out the blue light, the high frequency light, and they send it back in any direction. So technically it's sort of a reflection, but it's a process we call scattering. So whenever you see a blue nebula, it's a reflection nebula that's created through scattering. Okay, but if you want to call it a reflection nebula, go for it. It's okay. And then this here is an emission nebula. The red is an emission nebula. We have a little bit of wind. I can tell that our stars aren't perfect, so I apologize for that. You can look over my head. You can see the telescope is sticking straight up. It's like a flag in the wind. So that does cause problems at times, but we'll try to get through it. Right, so that's a reflection nebula, okay, again, created by scattering of starlight. And you'll notice the pretty blue color intermingled with this beautiful red color. That's really pretty. And it's the kind of thing that you could stare at all night, and say, wow, look at that. When you think about it, you're looking at a nebula that's, a light year or more long. That's pretty big. It goes down here and around here, it comes up over there. And you look at this little piece right here, and this little piece, it has an emission nebula on one side and dark nebula on the other. What that's showing you is that the hydrogen gas is all throughout this region, and it's mixed with the dark nebula. But on this side, the dark nebula probably is just dense enough to keep the starlight from ionizing its hydrogen that it's mixed with. So it effectively gives you this three-dimensional looking tendril here. It's really kind of interesting. But as we'll see, hopefully, if we can get to Orion after, we've got these beautiful pillows of dust. This is hydrogen and dust. But we can see these beautiful pillows of dust in between the Orion Nebula and the nebula above it called the Running Man. It's just stunning. Okay, we've stacked 23 here. That's good. So we'll stop this here. Okay, so we're going to pause it. And now we're going to save this. Just like we have it here, we should see the FITS file indicator in green, saying we saved it, and then we're going to see a similar indicator for the image file we're going to save. We're going to save this exactly as seen, and you'll see a PNG file indicator. There it is, right there, the PNG. And then we can clear our stack, get rid of our sandwich maker, and then go into the camera controls and go down and take our exposure back to 1 second. All right, and do our hyper shot where I actually increase the range here so we can see it like it's a finder scope, but with just enhanced vision. And now let's go back into our planetarium. So we're actually pretty high up there right now. Maybe while we're here, and again, I don't like, that's zenith.
Boy, the image quality via your Skype you're sharing with me has really gone downhill. Is that the laggy internet again?
Yes.
It's very blocky and pixelated.
Yes. Indeed. But we're going to, like I said, we just have to deal with it for now. Okay. Let's take a quick run over to the Pleiades. We're actually waiting for Orion to come up high enough because this side of the observatory right here, that's the eastern side. This is south at this end, north at that end. Telescope's pointing kind of toward the northeast right now, and north is more that way, all right, in the view. And this is the eastern wall of the observatory. And the telescope is a little bit toward that wall. And the reason I did that is because we're 65 miles from Phoenix, out in the desert. And although you can't see it with your eye, the telescope can see the faint light dome of Phoenix in the distance. So we want to ignore that. And so I set it up this way as sort of like you can't go here till later, meaning later on in the season or later on in the night. And it's worked very good. Plus, this has made room for 2 more telescopes in this building, putting it here. And so that's what we're doing. All right. So now we're going to head over to the Pleiades and show you the Pleiades. So here we go. So we're heading to find them. And you can enjoy the streaks that it makes. It's actually kind of cool. And we're going to use Zeta Tauri as the target. We're at like 100% here, so or 66%. So I'm going to go back down to auto. There we go.
Well, you'd think your high precision pointing, since the Pleiades are a cluster of bright stars, it would just go right to the Pleiades.
I know. But I actually had it do the same thing. When I told it to go to Betelgeuse at one point, it actually went to Bellatrix first and then jumped over to Betelgeuse. I don't know. Oh, well, see, Marianne, if you look at Marianne says, Mark, here in Benson, she's in Benson, Arizona, Orion is absolutely amazing bright. Yeah, it is. And if you actually go outside, Marianne, and look up at probably just overhead, actually, you're going to see the Pleiades. And they are the 7 sisters. Okay, more like the 100 sisters, because that's actually roughly how many stars are in here. Even more. But the 7 sisters here is going to be pretty bright as well, Marianne. So that's going to be right over your head. Okay. So here we are at the Pleiades. And you'll notice you can actually see some interesting cloudiness here. Well, that cloudiness is to what we were talking about earlier. And that is that these stars, all born in a cluster together, this cluster, in fact, along with some of these other stars you're seeing, are very bright and young. But they weren't born here. They were born elsewhere. And, like all objects in the galaxy, they orbit the galaxy. And by orbiting the galaxy, they move through the galaxy. And it just so happens that these stars are moving through a dusty area. And so their starlight is reflecting off the dust grains in here as well. And that's something, again, a reflection nebula created by scattering of that high frequency starlight, which is always blue. That's why these nebulae are always blue, because it's just that particular light that gets scattered. Yeah. Okay. So let's just do a somewhat short exposure on this. Let's just do 12 seconds on this and stack it. All right. Did I see a wind effect? Maybe I did. Let's find out. Yeah. Okay, we got some wind. That's what happens when wind hits the scope, see? So we'll clear that. Try again. Same thing. Got to keep trying. All right. We're gonna figure out a way to stop that. All right, so let's drop down to 1 second here. We had this problem in Orion last night, or the night before.
Yeah.
If you recall. Yeah, look at that. It seems at a certain time of the night, the winds, after sunset, the winds pick up a little bit. So here you can see, this is a live view. You're actually watching what happens when the wind begins affecting the telescope. Again, that's a giant sail, that big cylindrical cover on the telescope there, that big tube, giant sail. And so we get this. So it really becomes apparent when you zoom in. So let's, just for fun, let's go watch it's like a laser light show when you zoom in. Watch this. But it points out something I've told people back when we actually did Sky Tour live stream East out here with our dome. We're rehabbing East right now, and the telescope for it's behind me. But if you can't tell the colors of the stars, what you do is you actually take a photo where you allow them to streak. Okay? And when they do, the streaks show you the colors. Like, you can't really see the colors too well on these two stars. But when they streak, you'll see that this one's orange. And look at it right there. And this one's blue. See that? Orange and blue. Orange and blue. That one's orange. That one's orange. You know? This one is white. This one's blue. You know? So we actually have some wind out there, which is meddlesome, I would say. Meddlesome. That's all right.
If the Arizona desert is anything like the New Mexico desert, just wait till springtime.
Well, springtime, we could have some pretty high winds.
New Mexico desert gets really windy in the springtime.
Yeah, we could have some pretty good winds. I know that on nights or days where there's winds that are going to exceed like 80 miles an hour, I won't even remotely consider opening up. Because, you got wind whipped sand, too, that's going to come flying in, right? But tonight, we probably got 25-mile-an-hour winds out there, and they're enough to bounce it around a little bit. Don't worry, Marianne, I'm not going to ask you to head out to the desert. It's only a 4.5-hour ride for you right now, I guess, right? Maybe 3.5. No, about 4. But there you go. It's like a light show. All right, so the Pleiades are not going to cooperate for this. Actually, the weather's not going to cooperate for this. So we can skip the Pleiades. Let's see, Mark, did you ever side-eye the scope to use more of the... Yes. Weird guy saying, did you ever side-eye? That we call it averted vision, where in order to see something in the scope that is faint, and it's not something you do when you're doing digital like this, where you have it on the screen, but when you're looking at an eyepiece. What you do is you look at something, and you can't really see it when you look directly at it, but if you look to the side of the field, then you see it very brightly. That's called averted vision. AVERTED, averted vision. And the reason that works is, as Weird Guy was saying, is because the eye is composed of color receptors and black and white receptors. We evolved to have color receptors and black and white receptors. Dogs have far fewer of these color receptors and more of the black and white receptors, right? For instance. So what we have in our eye is a central cluster of these color receptors, and they're called cones, okay? And around the ring of the outside of the retina are these rods, which are black and white receptors. So if you want to look at something that's faint, oh, look, we got a satellite moving through the field right there. Check it out. It's kind of like fuzzy. Look at that. It looks like it had like a warp drive on it. Yeah. Well, anyway, so you look to the side of an object, and you'll actually end up seeing much more detail. All right? And that's because the cones are in play. I'm sorry, the rods are in play and not the cones.
Yeah. The Pleiades actually are a classic example of using averted vision. If you go out and you look directly at the Pleiades, naked eye, from a decently dark sky location, if you look directly at them, you will see the little dipper shape. If you avert your vision off to the side a little bit, you will see the whole cluster. You'll get the light of hundreds of stars, and all of a sudden it'll just jump out at you as a hazy patch of light.
Yeah. Here goes the satellite.
Mm.
It's a dash because we're doing a 1-second exposure. 1 second, 1 second. So if we did this for like a few milliseconds, then you'd see it moving as a dot, Okay. Well, now here's what happens. I've noticed that around this time of the night out there, 9 o'clock or so in the desert, we do get some wind, but it actually abates after a while. It goes away, which is really good. I'm glad that it does, because then that gives us time. So there's our Pleiades. We've seen it like this, and we're not going to get it any clearer than this, I can tell you that, until the wind goes away. So what I'm going to do is come down and see if we can go check out something a little bit lower. And by the way, make sure you do give us a thumbs up, all right, and subscribe if you haven't. Hey there, Papa Tom. What's going on? I haven't seen you for a while, man. I hope everything's all right. All right, so I'm going to zoom in here. See, right now our internet is more like we normally get. It's a little better. So let's see Actually, let's go here because I know we can see this right now. This is a cool little cluster. All right, here we go. We're on our way to this neat little cluster. And you'll watch the telescope moving over my head here. All right, as it heads now for a star that it's going to use as a guide post, signpost. Does that look like Betelgeuse?
Or Betelgeuse.
Looks like Betelgeuse, doesn't it?
Yeah.
Let's find out. If you look over here, you'll see, yep, see, centering Betelgeuse. So it's going to center Betelgeuse, the supergiant, the red supergiant, that if you put it where the sun is, it would go out beyond Mars, almost to Jupiter, in diameter. That's huge. In radius, I guess, if you consider it'd take up the orbit almost all the way to Jupiter. That's huge. Okay, now we're going to go to this really cool cluster. Here it comes. There it is. Right there. See it? Not yet, you don't. But you will. Let's hope that the wind doesn't kill it on us. Uh-oh. Looks like we're getting wind here now. Yeah, it's wind. We're done moving, but the telescope is still fighting wind. Yeah.
That's pretty bad.
Yeah. Well, this is a cluster called the 37 cluster. But we got to just get a moment of clarity so we can see it. You can see the 37, though. What did you say?
A moment of clarity. I think
Yes.
I see the 7. I can't quite make out the 3 yet.
Okay. Well, there's the 3. And here's the 7. Well, like I said, there's a period of time where the desert cooling that takes place causes winds to sweep across the desert. And it's this moment right now. It actually is it's over pretty quickly, though. It's only like a half hour, and then it's gone. So we're going to try and get through this. It's that cooling that occurs after sunset, and as the desert begins to cool, winds are generated, and it will go away, and we'll get moments of clarity. I mean, we had them earlier. We had all clarity, and then we started to get the winds. But that's okay. Those winds will be gone soon. In the summer, it's a beautiful wind. It feels just so nice. There's the 3. See it, Daryl? There's the 3.
Yes, I see them both now.
Yeah. The 37 cluster. A real oddball cluster, let me tell you. Why would we have a 37? I don't know. But it just goes to show you that pareidolia lives. Because this is just a happenstance of stars. It certainly isn't spelling out a 37. I'm doing that movement now.
You know, I've noticed, looking at the weather on windy.com, if I zoom in enough to see like the southwestern United States, so basically I can fit Colorado and Arizona in the same field of view, you know, and animate the satellite view, say. It's amazing. Arizona generally appears to be getting completely different weather than we are. That, you know, you'd think it'd be the same, but there you go. Yours is often down there around Phoenix. You'll be getting a west to east flow, either coming off the Pacific or coming up from Baja. And up where I am, it's usually coming out of the west-northwest, and it's just totally different weather streams.
Yeah, and that if you notice tonight, okay, this is visible. Let's do blue. Okay, if you notice, this is Arizona here, obviously, and there's not a single cloud in the entire state of Arizona. Not a single cloud. Now, this is part of the reason that I chose this elevation. That heart right there, that's the location of the observatory. It's at that perfect spot in Arizona, right, where, you know, it's far enough from Phoenix. Phoenix is way over here, right? But it's at a perfect spot where we get this gorgeous sky, and you can actually see all the way down almost to the horizon with some reasonable clarity. That's not the case wherever you go. It's not always the case because you're always seeing through more air. But this is an example of what happens when you look through. Get back here. This is an example of what happens when you look through a telescope in the middle of a desert in a very clear area. Our skies out here are what are called Bortle 3 skies. Bortle, B-O-R-T-L-E, named after the guy who came up with this system, but actually is an amateur, and it ended up getting adopted as a pretty good way to classify the sky. Downtown Phoenix, the sky would look white to you in a Bortle. It would be like Bortle 9, okay? And it goes 8, 7, 6, 5, 4, 3. The skies here are Bortle 4, Bortle 5. The skies in Arizona, where we are with the telescope, is Bortle 2/3. So it's very, very close to being hard to see in front of your face, okay, when you walk. In fact, you got to use a flashlight anyway at night because you can't see all the problems with the ground. You just can't. I've told the story. I was walking back from the observatory. I was going toward the house out there. There's a house out there on the property that we're on. We're on protected property. And as I was walking away from the observatory, I looked to my right and I shined a light. And keeping pace with me is this big rat running along the ground. Dunk, 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 dunk. Okay, they grow big out there. And then I turned the light to my front and looked down. And right there on the ground, as big as this hand, was a tarantula. And he was on the prowl. And he saw me, or saw the light, and he ran into a hole. Bloop. The hole was no bigger than my thumb in diameter. And this tarantula, that big, squeezed into this hole. It's like, how in the heck does that happen? I guess it comes from having all soft parts. You know, just like octopus. An octopus can go through a space that's, just about as small as its beak. That's the only hard part on the octopus is the beak inside where all the arms meet. You've got a hard shell beak. Well, it can squeeze through openings that are just a little bit larger than its beak. I guess same for tarantulas. But it was a really pretty animal. It was sort of a black and red tarantula, rusty color red. It was beautiful. Okay, see now the 37
we get
clusters.
tarantulas here sometimes.
Yeah.
There are some places here that are famous for them, especially during mating season. They have like a migration of the tarantulas. All the tarantulas set out with the same thing in mind. It's a hey baby time, and you just get
you want to go to 7-Eleven.
Massive migrations of tarantulas, all headed out for the same reason.
Mm-hmm.
I'll just leave it at that.
Yeah, I think we know what is happening. Okay, while waiting for the skies to calm down, you'll notice we did have some moments of clarity there. So I think we're getting past the sunset wind right now. Let's see if we can zoom in on this a little bit. This is just a 1 second exposure we're just looking at directly. Let's go to 75%. And it'll still be rough, but once it comes into focus, you'll see the 37 clearly. I mean, you can see it now. There's the 3. There's the 7. Yeah, so that's pretty good. Very cool indeed. All right, let's check out a few other things here. Based on the height of the telescope, I would say we should be able to. I'm gonna do this too. I'm gonna head down to Hubble's Variable Nebula. Hope I can make it down that far. I think I should. I can make that. Because Hubble's Variable Nebula is a very interesting location, and we're gonna check the nebula. There's a lot going on around Hubble's Variable Nebula, and we might want to check that out. I'll show you the rosette maybe if we can, but you know, people want to see lots of cool things, so maybe we can show them the Orion Nebula too as well. Now we're going to Alzir. Alzir is the star that we're slewing to right now, and it's the star that's going to be brought into the middle and used as our signpost and guide to the location that we're going, which is Hubble's Variable Nebula. And let's hope that the angle of the telescope tube keeps us from having to worry about the has to keep us from worrying about the wind.
If you get Hubble's Variable Nebula, which I see right there, and if we can see the cone and the Christmas tree too, which is just up to the upper left some.
Yeah, I'm gonna do just Hubble's Variable Nebula right now.
I understand, but if we can go up there, I can show you the phosphor.
Oh, okay.
Mentioned the other night.
Yeah, we talked about that the other night. Okay, I'm gonna center up Hubble's Variable Nebula. This tiny little thing right there. All right. All right, and let's. Well, it looks like we're getting some wind-free images here. So we'll wait for the 11 seconds and see if we can get. We'll do a 10-second shot of this, and that's gonna overexpose it. And I can see that the wind is now picking up as soon as I mention it. Okay. Well, we can try it. Here we go.
Excuse me a moment, please.
Sure. Okay. Okay, that's premature, I guess, in trying to get that photograph clean. Gonna clear that again. Let's try again. That's not clean. Gotta do it again. It's all right. We're at that stage where we're trying to get this not clean, but I want to show you anyway what's going on here. We're going to go to 75% of this. That little tiny thing is what we're looking at. Okay. It really looks so pretty when we get a nice clear shot of it. And then we will. You'll see. I am determined. I'm going to get a clear shot of this. I will not be beaten. Okay, maybe I will, just a little. Try again. Everybody down. All right, here we go. I can try reducing the exposure a little too. Yeah, this is just very bad. Let's try. Actually, try a 3-second shot. 3 seconds could do it. Let's try that. Eek. Look like bugs squashed on this. Wow. Yeah, okay. As we can see, the wind is still in play out there. Comes and goes. Telescope's actually mounted very well out there. It's on a big steel pier. And that steel pier is 24 inches tall. And the telescope rises another 30-something, 40-something inches above that. Just about. So it's actually... but it's all very rigid. But again, when you got this gigantic flag up here that blows in the wind, it catches it. And what you're looking at is these very slight motions. But again, you can see the colors of the stars. That's another thing to look at here. That's kind of cool. So yes, this is not the prettiest thing, but you can see how this location in space, look at the colors of the stars. It's actually kind of a good teaching moment. We can actually see how the star colors change out there. You know, and that's Hubble's Variable Nebula right there. All right, let's try again. Yeah, not quite. Let me just do that. Too much. I want to get rid of that noise. Too much. That's good. All right. And we'll clear that. Just trying to get a good one shot of this. Yeah, okay. Not yet. Actually, Vera mentions, Mark, you should install, or you could install a wind meter. Better than that, Vera, I actually want to install a weather station and make it standalone. There is a weather station on the property that I could use, but it's not something that's readily accessible, but it's okay. Yes, Louis Ta says it looks like a comet. Yeah. If anything, you just look at the star colors that are created by this thing. You can actually see how many different types of star colors there are. Notice also, none of them are green. There are no green stars. That has to do with the way radiation works. It has to do with what's called the black body. And we go from blue hot to white hot, right? And from white hot to yellow hot to red hot. Okay, so when you see something really hot, it's blue, like the base of a flame. And as you follow that flame out, it goes through all the rest of those colors until it's a kind of reddish orange. And so that's what we see with radiation. We don't see green in there. The only way you see green, and not in the universe, but in general in the chemistry lab, is if you actually do something with the element copper. You'll see a green flame, and you'll see some meteors that might have some green tint to them because of that. This isn't Daryl. There's a lot of wind.
Yes,
so
I see
I've
that.
been trying to get one clear shot so I can show this. See, it's getting there, but we're gonna need more than one.
Yeah.
I'm just doing 3 second shots right now. We'll get a moment of clarity.
See green in oxygen 3, of course.
Yeah, but I'm not talking. And we're talking about that's an emission, though. That's not, like a starlight spectrum.
Yeah. Some people
But there's no
who
green
see
stars.
some people who see the secondary of Antares and Scorpius claim it's green, but that's a contrast effect. It's actually kind of a blue color.
Yeah, when you see a very, very bright orange thing in the sky or a red thing, your eye can be fooled by the color you think you're seeing for the much less luminous part.
Yeah.
And that's what we're seeing. You know, so that's pretty cool. Oh, I'm trying, guys. What can I tell you? I'm trying. We're just gonna have to wait it out, I guess. Now, if I go up to the cone, you know what's gonna happen? It's gonna get even worse.
Why?
Because we're gonna raise the flag even higher in the dome, in the building.
Oh, that's just a hair up higher.
It's not much. You're right. But unfortunately, we have to take an exposure that's going to be, 30 seconds.
Yeah.
And this is 3. This is 3 seconds, and it's not able to support it right now with the wind. I will say this, okay? Other observatories, okay, they will actually close down when there's winds like this. And this is why, because they can't get clear shots. And I'm actually on the verge of thinking about doing that for tonight. But this should abate. We do usually get, by the time it's 9:30 or so, those winds should be easing off. So I'm going to give it a few more minutes, and we'll see.
You want to talk about secondary stars as we wait for the wind to go away? You may have heard this before. I'm sure you have, Mark. Others may have. The secondary star Sirius B to Sirius A, the brightest star in the sky. It's a little, well, I guess Sirius B is a white dwarf now, isn't it? Yet, some say they wondered what kind of time frame it could have happened that Sirius B became a white dwarf. Some point to the ancient Greeks supposedly described Sirius as ruddy in color, which means red.
Yeah.
Yet we see Sirius nowadays, and it's kind of a bluish-white star. Plus, it twinkles a lot. And some have speculated whether they could have been seeing a Sirius B before it turned into a white dwarf. But the time scales are so great that most astronomers nowadays would say that's not possible. And then again, on a slightly different tack, I forget which tribe it is, but there's a tribe in... I'm sorry?
The Dogon, D-O-G-O-N.
Oh, yeah, okay, the Dogon. In Africa, their cosmology, I guess you would say, or their astronomy, they all seem to be well aware that Sirius has a secondary star. They were never taught Western astronomy.
Yeah, I've always been intrigued by the theory of the Dogon. I will say this, when a star goes to a red supergiant, for it to shrink down, it's not going to shrink down in just 1,000 or 2,000 years.
Right.
It's going to be in that state for 10,000 years or so. It must be realistic to say that, say, Neanderthal saw a red star for Sirius, but not. Of course, we have no history then. But it doesn't make sense that more modern humans would make that claim. It just doesn't. But let it be said that the universe does surprise us. Like with those filaments, the story you sent, which is the filaments that we see in the center of the galaxy, of our own galaxy, that are moving out. It makes our galaxy a very interesting location. you know?
Yes. Uh, uh, what Mark's talking about, folks, is some recent. I'd have to go look it up again. Uh, they're radio frequency images of the center of our Milky Way galaxy, and
Yes.
they're wide field. And uh, do you remember the name of the project, Mark? I could go back and look into where I sent you that earlier. Uh,
Yeah, I will find it.
um, they're just amazing images, but they are taken in radio frequencies of what's going on a large scale in the galactic center. And I mean, there you
Well,
go. There are loops and bubbles and those filaments all over the place. Can you click on that picture? It may go bigger.
yeah. This is first of all, some of these filaments you're seeing here were known in a 1980s study, but the rest of these filaments and the rest of this structure was not known. This is all new. So the Meerkat telescope, which is in Africa,
That's it.
is what imaged this. Yeah, Meerkat. And the scientists that actually looked at this, this was the South African Radio Observatory, SARAO, SARAO. He is, what's his name? Yusuf Zada. He's the one that did this. So that's very interesting. So again, there's so much that's going on with our local universe that we don't even understand. It's incredible. Let me do another check here.
As I said, I said earlier, or before the stream, that we've talked about multiple spectra images before. You know, like they combine visible and X-ray or infrared and whatever. Once Webb gets going, it would really be interesting to see what they can come up with when they look toward the center of the galaxy in infrared, and then mate that to the radio images. What that may show us.
Imagine.
What's hidden by dust right now.
Yeah.
I think that was just an amazing image. All those filaments and stuff.
Yeah, we're living in that.
Uh-huh.
Okay. This is get rid of the stack because just want to see if we can get past the it might be adiabatic cooling or something going on. All right. Daryl, if you don't mind for a second, I'm going to go grab a water. I'll be right back.
Sure.
All right. I'll turn up the music.
Keep people entertained.
Oh, we're waiting for the wind. Yeah, I'll be right back.
I wish I could share pictures with you folks. I would try to show you stuff while Mark's gone. There was another image from that same survey, that radio image from the center of the Milky Way. It wasn't in color, but it was a much larger image, much more detailed. And you could see a big bulbous supernova remnant that when the star exploded, it got blown sideways right out of the bubble of the supernova. It's racing away off to one side now, and the filaments, and it shows you the area of Sagittarius A star, the supermassive black hole at the center of our galaxy, stuff like that. Sounds like he's back already.
Oh yeah. Well, I just have to go outside my little office space here, and oh man, look at this. I went to a half-second exposures, so you could see a little bit more real time what's going on. I'll go to quarter-second exposures now, and then pump it up a little bit more. So now it'll be 250 millisecond exposures. And then it'll be faster updating. All right. So now you can see that's more real time. And I can just give us just a little bit more brightness here.
Can I ask you a question?
Yes.
Don't get mad at me. If you had a dome instead of a roll-off roof, would that help with the wind?
Yes. However, but I wouldn't be mad because I gave up the dome here for this similar reason.
Yes.
A dome is great for a singular telescope, but if you're planning on having more than one telescope,
Yeah.
you can't use the dome. The dome has to be in such a way that the telescope is centered under the slit as it moves around. So that's a one telescope, one dome. But this building here, this is going to be a multi-telescope facility. So it's going to have more than one system in there. So we need to have the roof go away. That's all. I mean, and that's the reason. You know?
What if you could erect windshields as the need required? Wind screens, let me say.
Yeah, I believe it or not, you're gonna laugh, but I actually did think of that. And then when I studied the way the wind flows around those windscreens, we would end up with more turbulent wind on the far side than to just leave it open. You can see this. You can see this when you have a piece of paper this big, and you have a candle right here, and you blow on the paper. The wind goes around, and then laminar flow goes right around the paper and puts out the candle, even though the candle is behind paper. So, and it comes in at a more accelerated from two directions, not just one. I know, physics, man. I don't know. It gets in our way. Okay, well, you know what? Maybe in this direction, things aren't that hot. But let's try something else. All right. All right, tell you what. Let's take the telescope down south a little bit, and let's see if this works. Here we go. Bring it down.
Orion's probably pretty much on the meridian for you now.
Yeah, I think we'll be okay for that. But let's just try. Let's see if this even works. Because what I'm bringing in now, of course, is La Rosette. And let's find out if we can do it. Yeah, there it is. Technically, I should be just instantly closing down this dome, but I don't want to. I want to give you guys something to look at for a bit, if I can. Okay. Yeah, it doesn't... yeah, we're getting lots of wind. Okay. Let's try Orion, okay? And let's see if we can look down in that region.
I'll try for the 13th Pearl again? What we talked about earlier?
Yeah, 13th Pearl. I mean, but of course, people want to see the Orion Nebula too. So let's just go there first, and then we'll drop south of it and check out the 13th Pearl if we are allowed to by the wind.
Sure.
It's actually going to be... this might work out. Alright, so let's go into the Great Nebula in Orion. Okay. Here we go. Okay. The system is on its way. And we're heading to... Let's find out what star we're heading to. Cursa. Interesting. I think the star we're looking at is Cursa, and it's auto-centering it. Right? But then it does something weird. And this is not our fault. This is a database issue. And that's it. And then you're going to get another bright star that's going to... Oh, okay, here's the Orion Nebula. That worked this time. Yesterday, when I was doing this private stream, I could not get the Orion Nebula to come in properly when it went to Cursa. It would actually go to the wrong location and leave me far to the east of Orion. And I had to just move the telescope back. Anyway, okay, so let me just center this a little bit more. I think that we're going to end up with a lot of still have issues. Look how high the telescope is looking, though. Right there, you can see the telescope's really elevated pretty high for the Orion Nebula.
Yep.
So at this location, the Orion Nebula is it's at an altitude of like 50 degrees, above 45 to us. Okay. Well, whatever. I'm going to try just a fun little exposure. Let's say, let's just try and do a 4-second exposure of the Orion Nebula and stack it. It's probably going to be terrible, but we'll try it. Okay, it's a windy night, I guess. This is something that happened that I did not expect, so that's okay. It can't always go our way. Yeah, okay. Let me get rid of... Oh, and as always, we've always got satellites now going through Orion. I've never been able to take a photo of Orion without all these satellites going through. That's actually a pretty shot, even though it's got satellites in it. And although the stars are elongated out of the way wrongly. So we'll clear it again. Try it again. Oh, worse. I'm trying, guys. But I can't control the weather. It gets even worse. Okay. I'll tell you what. Let's stop the stacking process and just look at the individual shots. Look at that. We got 1, 2, 3, 4, 5. And then, what? Almost 7 satellites at a time heading through here. Wow. This is 4 seconds. That's now you can see why astronomers have been up in arms, because it turns out that the satellites are literally very, very bad for doing any kind of astronomical observing. See these 3, and then we got 1, 2. This looks like a Starlink train that's actually been starting to lengthen out. I think we caught a Starlink train. Look at them all. This is a Starlink train. Holy cow. That's pretty cool. Look at them. We gotta capture this. Oh, we are capturing it. We're streaming. Okay. Izabela, when you do this, make note possible Starlink train at this time. Okay. Because you can see them all. Look at it. They're right. They're spaced behind each other. That might be a Starlink train.
As you said before, though, I mean, and as Donald notes, they look like equatorial orbits.
Yeah, but
Starlink,
they initially... Yeah, go ahead.
Starlinks tend to move diagonal.
Yes. However, it could be that when the Starlink train is first released, they might be in such an orbit, and then they are going to individually change their orbits as they move into the different orbital paths. and it takes time to move into those final paths. Weird guy, good night. Thanks for dropping by. Sorry the weather's not really working so well with us tonight. All right, so that's cool. Believe it or not, I have yet to actually see a Starlink train. Unless I just saw one.
Oh, I've seen them several times.
I have not.
It's interesting. I think my curiosity was satisfied after seeing it a time or two. It's neat to see. People, general public freaks out every time, there's a new Starlink train. Oh my God, what am I seeing? And, there must be UFOs. And somebody has to
I get a few of those.
Quiet them down.
Yeah, that's usually me. Just explain to them that, it is something very odd that you're not used to seeing. Yep. So I don't feel ill of people. I don't think ill of them for not knowing. They're fascinating. I remember the first time I saw a sounding rocket launch. I never knew what it was. Hey, Laura Newbert. But the sounding rocket launch left these beautiful chemicals in the upper atmosphere to interact with the solar wind and created these beautiful purple and blue circular patches in the sky. And it was really, really impressive. And I remember calling down to like Washington, D.C. to a alert network and saying that I'm seeing an astronomical thing in the sky. This was when I was actually probably in high school. And they said, well, they'd launched a sounding rocket from Wallops Island, and it's releasing barium or strontium in the sky, and it's actually going to make these false auroras because they want to test how the upper level winds are moving subject to the solar wind. I was like, wow, that's so cool. So, yeah, I can see. Well, let's try something here. All right. I'm seeing a moment of clarity. Let's try a 20-second exposure. It's going to overexpose everything, but I want to just see if we can grab something. We'll stack right away. I'm going to do this right away. Yeah, that's the previous nasty one. Okay, let's get in here. And clear. And then this image will get read out off the chip. And let's see what it's going to look like. Did we luck out? Yeah, we kind of lucked out. Look at that. Yes, it's overexposed. But what I can do is I can make it look a little better. So it looks like we got round stars. I'm wondering if we're past the cooling period in the desert right now. Oh, look at that. That's really pretty. And I wanted to show you this section right here. That's where I want to go. Of course, the Orion Nebula is stunning in its own. The red is, of course, due to ionized hydrogen being caused to glow by what's inside this brightly overexposed central core. These stars are ionizing this hydrogen all around for several light years. And the ionized hydrogen will glow red. There's also oxygen in here, this bluish green. This is oxygen. And that is glowing that color because oxygen is being doubly ionized twice. Hydrogen can't be doubly ionized. It can only be singly ionized because it only has one electron. Oxygen has a few more. So, And I take pictures of the Orion Nebula like this because, and I do it routinely because I'm wondering if there's ever any changes, like a new star winks on or something. We might be able to see it. When a new star, like it pops in down here somewhere, it'd be great to be able to see that and say, hey, look, that wasn't there before, now it is. And then we'll be co-discoverers, or any one of you will be. If any of you actually analyze our previous imagery and start going through it, you might find something. You might, and that might be pretty cool. Okay, now let's go in here. Let's go to 75%. Okay, little wind issue. Okay, this blockiness is just... in fact, the wind could be causing some issues too. With the Viasat. That's another thing I didn't think of. The wind, is operating. It's also hitting the satellite dish too. And it could knock the satellite dish a little bit, causing it to momentarily lose connection, which is why we might have lost our connection earlier tonight for a brief moment. Just as long as it doesn't get knocked down. Yeah, Vera, it's like building a library, isn't it? Okay. Vera, you're watching this on a cell phone? Oh, man. I'm sorry to hear that. You're missing such beautiful panoramic vistas. Not really. Tonight with the wind, it's a little bit difficult, as you can see. Okay, now we're gonna go back out. Okay. I won't say this because it's really not focused well because of the wind. But we'll clear it and go into, instead of 20 seconds, let's just do 5 seconds. Okay, so now we're gonna get a 5-second shot. Look at that, it didn't work. I mean, obviously the wind came back.
Huh.
That was pretty cool. We got in between, Yeah. Grr. Okay. Well, I'm not pleased, but it is par for the course, unfortunately.
You gonna call it?
I don't wanna, but I think I need to. But in any case, this is what we were trying to take a picture of, guys. Measure 42. Okay, hold on a minute. I don't know when to say, I don't know when to give up, you know that. But I can see that we need to. This is also ruined. Let's clear this and see if we can get another shot here. Yeah. Okay. Folks, I'm sorry, but apparently the desert has the winds tonight. Normally it's gone. I guess maybe because I started at 9:30. I probably could have started at a little earlier, but the sun and the evening twilight is gone by the time we started. That's when I did it. Okay. All right. Well, you know what? I guess I'm gonna have to call it. I'm sorry, folks. Yeah, So, we'll try to make up for it tomorrow if it's clear. All right. So that should be okay. I mean, there's not a cloud in all of Arizona right now. But I want to thank you guys for joining me here, and Daryl and I both are not happy this is the way it's going, but it is the way it's going. We can't even show you the thing we wanted to show you down below, down here. But I guess that's the way the cookie crumbles, right?
That's the way the cookie crumbles.
Yep. Yeah.
Could be worse. Could be snowing.
That's true. You know. Which is what it's probably going to do for me this weekend. Not 3 feet, though.
We'll see.
Yep.
That's supposedly the storm that just went through here, I guess.
Mm-hmm.
Get to you by the weekend.
Yeah. Okay, well, at the very least, I can do the shutdown procedure anyway. So the first thing that I do is I disconnect the planetarium system from the computer and from the telescope. And I will leave that behind. Alright. And then, of course, the planetarium itself can go. The nice thing is, it stayed focused all night. I had it on a mode where, it was, as I've told you before, where it's changing focus with the temperature change, and it actually kept up with that. It did a very nice job. So the focus now, let's see what it's set at. If it comes up. Alright. Yeah, 48,101. Yeah, let's see what the temperature is in there. 52.9. Alright, that's consistent. Very good. Alright, so I'll disconnect the focuser. Boy, look at that. Dancing around like a no tomorrow.
Okay. I'm going to call it a night. Everybody, thanks for coming. Take care and have fun, and hope to see you all the next time. Mark, thank you for having me, and
sure.
Keep your fingers crossed. All righty, have a good night. Bye-bye.
There's still a couple of good ones up there, so that we got before this.
Yeah.
But so they're up on the server. All right, guys, and thanks, Daryl. I'll talk to you again.
Okay, take care. Good night, everybody.
All right, good night, Daryl. Okay, so that said, we will do our best to see. I'm holding out all hope, still dancing around. I guess the wind has been a problem. Okay, let's see where we are. Okay, this here. Okay, now what I can do is park the scope, and the parking process is very simple. The telescope is going to move to a location where it is what we call safed. Okay, SAFED. It's in safe mode. All right, and that's this position. You'll watch right there. It's going to say slewing, and then it's going to say turn the scope off. All right, and I actually have the program I wrote to control the observatory is down here in the lower right, and now you'll watch this go off here when I tell us to turn it off. So ready, go off, and now that goes off. So the telescope is now safed off, and I can literally close the roof right now if I want to, but I'm going to disconnect the scope first. You do everything, it's a reverse order from what I when I started it. So now that I close this. Okay, the camera's still connected. I always leave it connected to the end, and then it's the last thing to be disconnected because I want my camera to be working, have the eyes going on and that building all the time. Okay, now this can close and leave us with our desktop and just our view into the telescope. And now what I can do is close the roof of the telescope. And there we go. You'll watch the roof start to move across. There we go. Good night, telescope. Nobody wants to see it go. So yeah. Well, it was a good college try. And we'll do it again. Tomorrow, if it's clear, we'll be back here at it again. The wind is actually rare out there, so there are days when this happens. But thank you, guys. And now that that's done, I can close all these things and get out of all of these that I've got going on. And close my Observatory program. And that is it. Well, thank you, guys. It was great to see you. And we will talk to you again, hopefully as soon as tomorrow. All right? See you guys. Have a good evening. I'll talk to you very soon. Bye-bye.